Okay, yeah. So hopefully you guys can come in the Kahoot. You can still scan the top QR code. We'll wait for, let's see. Hengchang's back. Welcome back. 15. Let's see whether we can get 15 people instead. Ten, 11. There's at least several of us on Zoom, so hopefully we get to 6, 11, 12, 13. Two more. 14. 15. Okay, I think we're ready to start. Let's start when you're ready. Good luck, everyone.
So we'll start off with an easy question. Yeah, so this should be an easy question. So let's go to the next question.
Somebody's fast. Okay. Multi-select.
What are some of the disadvantages of transfer learning? Yep. So all of them are correct. So domain mismatch is when transfer learning is most effective when the source and target task domains are related. If they're too different, transferring knowledge could even be detrimental to performance. For lack of interpretability, it can be challenging to discern how much of the decision making is due to the source task knowledge and how much of it is due to the target task data. For dependency on source task, if a pre-trained model has bias or issues, they can propagate to the target task. So let's go to the next question. What is transductive learning or transfer learning? So the presenter showed two types of general transfer learning, transductive and inductive. Transductive is same task labeled data only in source domain. Inductive is different tasks labeled in target domain. Sequential transfer learning. What is it? Okay, I thought this would be easy because yeah, this is directly from the slide actually. So yeah. What model does this represent? Yes, so yes, it's Elmo. So the presenter showed two types of models, Cove and Elmo. In Cove, we are taking hidden states of only the last layer. In Elmo, it's taking all the layer hidden states into the generation. What is the goal of dialogue state tracking, a dialogue state tracking system? So what the presenter said is dialogue state tracking system is a core component in task-oriented dialogue systems, such as restaurant reservations or ticket booking. The goal of a DST is to extract user goals/intentions expressed during the conversations and to encode them as a compact set of dialogue states. Example, a set of slots and their corresponding values. So what are the benefits of meta learning? Okay, yeah, 8 was something I just came up with, so that was a trick question. So that was a trick. So what the presenter said is learning how to learn any task is basically knowing how to learn specific tasks. Acquiring the correct features more quickly from smaller data sets is extremely effective in few shot learning, generalizes better on new tasks. Much more generalizable across tasks is in a sense quite similar to multitasking, and for LLMs, it implicitly uses meta learning. Okay, so this should be the last question. So this is for double points. So if you are behind, you can come back with this. So this equation was presented by the meta learning presenter. I think 1 divided by D is basically the average. X is the text input and C is the class. Tree. Yeah, that's kind of interesting because presenter only showed one formula, so it's only for one of them, but maybe people forgot. So let me just iterate again. So basically the presenter was asking how can we transfer knowledge across distant domains with different classification targets for PLM-based text classifications. So he gave 3 types. The first one is actually task representation learning. So it employs the idea of prototypes and similar task classes towards one prototype. So that formula was for that only. And the second one was multitask meta learner training. It represents prototype vectors in a meta-knowledge graph. And number 3 was task-specific model fine-tuning. Fine-tune our meta-learner for original tasks. Yeah. So congratulations to the people who got it right.
Also, thank Liong for composing today's Kahoot. Thank you so much, everyone. Do you need? Since you're
Yeah.
right? Okay. Close this. And so, as usual, we have the scribe document, so somebody can put that in the general channel for all of you who have laptops that want to contribute. I want to remind people that I still have some 6101 PhD students who are not assigned to a project, and that is a little worrying. It's already week 11 next week, so we need to make sure everyone who is taking CS6101 as a PhD student is assigned to a project, and that you're working with a group on that, and that any of our undergraduate students doing it for CP3106 has been assigned to a project. So if you haven't done that already, please do so. Again, this week is development sprint 2, sprint 3 was due last week. So if you haven't actually finished that, that's fine. Just make sure you do that and bump in your thread that you need comments from me. Michael may decide to comment on your project if he's able to, but I will definitely go through each project. I'm a little bit behind due to other administrative work for our school, but hopefully that will be taken care of soon. Okay. So without further ado, we'll have our presenters. We have a very big group of presenters today, and 1 hour and 40 minutes to clear everything. So let's hope for the best, okay? Do try to discuss. So we'll try to leave at least 5 minutes between every section in case there are questions. I feel that the question session is actually more valuable in some cases, okay? So thank you all ahead of time, presenters, for your work. Let's have Alson.
Right.
You want to go to slideshow mode? Yeah. Let's see whether does the clicker work?
It's okay. I'll just
Yeah, sorry about that.
No.
Okay, Alson, take it away. Thank you.
Okay, so a very good afternoon, everyone. This week's topic is on retrieval-based LLMs. And the presenters for this week are myself, Alson, Qijiong, Tongyao, Hengchang, Winston, and Jiaxiang. So I'll be opening today's presentation with an overview and the benefits of retrieval-based LLMs. And my partners will be talking more into the technicalities and the nitty-gritties of how retrieval-based LLMs work. So now let's dive right into it.
Can you just check the chat there? I just want to make sure there's nothing in the chat. So.
Here?
Okay, no problem.
Okay. I close it?
Yeah.
All right. Okay.
You just click on the slide. Yeah.
Okay, so let's dive right into the benefits of retrieval augmented LLMs. My part will be more beginner friendly. I'll just be talking about like the introduction and overview, so I won't go into like the math and the details. Yeah. Now, in order to talk about the benefits of retrieval augmented LLMs, we'll first have to understand a little bit on the problems with relying solely on conventional LLMs. So first, they require a large number of parameters and massive computational power as a result. Next, they tend to hallucinate. They can generate outdated or incorrect information. Third, they are unable to verify generated information, and that portion of verification is left up to the users to go and search up on their own. So this brings in retrieval-based LLMs, which can help to solve these issues and more. So there are a lot of benefits, but I'll just cover 2 papers today. The first is that retrieval-based LMs can outperform LMs without retrieval by a large margin with much fewer parameters. And I'll present this paper by Marlon et al. They evaluated 10 models with varying scale and size, OPT, GPT-Neo, and GPT-3, against a simple template of question and answering. They defined factual knowledge as a triplet of subject, relationship, and object. So, like, what is the capital of Louisiana? And then the answer will be Baton Rouge. So they want to find out how accurate these models will be. Very simple. They evaluate these models on the data sets, NQ, entity questions, and they made their own data set, PopQA, by sampling knowledge triplets from Wikipedia. They have also this thing called popularity calculation, where how popular a question is defined on how many Wikipedia monthly page views there are on the particular topic. Okay, so in short, the results are as follows. The more popular a question, the more accurate a result will be. And they hypothesize that that popularity can be a reliable indicator of LM's factual knowledge memorization. The larger the LM, the stronger this correlation. And so how, you might ask, that we can achieve better performance? How do we get higher accuracy for all questions, regardless of popularity? Do we make the model bigger? It is found that scaling does not actually help with less common knowledge. Most of scaling's positive effects comes on the parametric knowledge. Most of scaling's positive effect on parametric knowledge comes from questions with high popularity. In that sense, I would like to point out on the image that the lower popularity questions actually do not see improved benefits when it comes to scaling the model. And quantitatively, so the three models, GPT-Neo, GPT-3, Da Vinci, have like 15%, 16%, and 19% accuracy on the least common questions. Okay. And so this is where we bring in...
Can you use the laser pointer? Can you press L? Yeah, and then move the cursor. Yeah.
Oh, okay. Thank you. Okay. So this is where we bring in retrieval. So this is where we bring in retrieval-augmented LMs. So they used BM25 and Contriver. And you can see that for the four models, these are quite small models, the accuracy actually improved drastically. Okay, so the results I would like to point out, most importantly, is that for the least popular and common questions, they actually see a much drastic improvement using retrieval augmentation. So the takeaway is that a much smaller LM, like a GPT-Neo 2.7b, augmented by Contriver retrieval, actually outperforms vanilla GPT-3, which is a much, much bigger model. However, there's a caveat. For 10% of the question, retrievals may not always be correct or helpful and can actually mislead LMs. And retrieval-augmented models suffer in more popular entities because the paper actually mentioned something a bit about the parameters. If the model is big, the parameters can actually memorize a lot of the more popular questions answers. And then if you retrieve low-quality text, it will actually confuse the models instead. So now, in summary, they propose something called adaptive retrieval. In essence, it is retrieval only where it helps. So smaller models can afford to retrieve more to compensate for their smaller parameters. And secondly, adaptive retrieval also reduces inference time costs. Because if you know that you do not have to retrieve something and you can just pull it from your parameters, then you can do that. And then it actually reduces the overall processing time. So that's all for this paper. Let's move on to the next benefit. The second benefit of retrieval-based models is to actually provide citations for users to verify and evaluate predictions. So the onus is not on the user to actually go and verify his own information, but this paper actually proposes something called Gopher Cite, where it will actually give specific quotes to back up the claims generated by the model. So Gopher Cite is based on the 280B parameter model by DeepMind Gopher. And it has fantastic results, 80% on NQ and 67 on Eli5. But I want to point out an interesting note is that you can abstain from answering questions. And abstaining from 1/3 of the questions actually improve accuracy to 90% and 80% respectively. But there's another interesting point that I'd like to point out, is that not all claims supported by evidence are true. And that just because you can support your argument does not necessarily and automatically make it true, which I will show more examples later. And this paper is by Manik et al. Okay, so they define the accuracy with these two words, plausible and supported, under this self-supported question answering, SQA. So plausible actually means if the answer is reasonable, is it humane? Is it a common response, a normal response that a human will give? And supported, whether that response can be backed up by evidence from somewhere else. Okay, so plausible and supported. So a little bit about how they train is just they train the supervised fine-tuning model, they also train a reward model, and they also optimize the reinforcement learning policy. But the point is the training data is actually labeled by human raters. And I'll show you how it works later on. So in real time, the model actually does all this, but the attention will be on 4 and 5. The reward model actually pulls the highest rated, highest reward answer and present it to the user. And then these preferences are actually trained by humans. So they train it using this template. Once again, bringing up the plausible and supported notion. So this example is like who played Rachel in Friends, and then there's two answers. Both are Jennifer Aniston. But this is the sources that they pull out, which is the key point. First, the first one is this thing, blah, 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 portrayed by Jennifer Aniston. So this is actually a plausible and supported answer. It is a good response, a natural human response, and it's also supported by evidence. However, the second example, actually, it is a supported example, a supported response, but it's not natural. You won't talk about a person's biography when you're simply trying to ask, did this person play this character in a particular movie? So the idea of plausible and supported, once again. Okay, so they also talk about the similarities and differences with recent works. They pointed out like Lambda by Google and WebGPT by OpenAI. But I would like to just point the attention to how they present evidence. So GopherSite actually can give you specific quotes to back up the claims, as well as there's a threshold for the I don't know, the abstention. And playing with this threshold actually improves the accuracy, and we can see that a little bit more later on. In the sense of information retrieval, GopherSite is trained on much longer documents, while the, I guess, related works are trained with shorter fragments and paragraphs. All right. So with all that, this is what they found, is what I talk about. They scored very well, 80% on NQ and 67% on Eli 5. This percentage is not only like how accurate, but also plausible and supported. Next, declining to answer substantially improves results. So basically, they can do a trade-off between the quality of responses and when the system does, the percentage of questions attempted can be traded off with the quality of responses when the system does attempt to answer. They developed 3 scoring techniques, but yeah, we don't need to get into that. And next, this is the main caveat I was talking about at the start. The models show no improvements in truthfulness per definition from the truthful QA. So what is this truthfulness definition? It actually means that a claim counts as true if it describes the literal truth about the real world, and informative if it provides information that reduces uncertainty raised by the question. So on the top example, what does drinking Red Bull give you? It gives you, they will say it gives you wings. Well, it is a plausible response and it is supported by evidence, but it's not literally true. And this is what they like to point out, is that the model do not have that mental acuity to discern what is actually true and what is, maybe just an advertisement or something made up. And of course, the last example, the one very big, is like, what do the lines on your palm means? And it means you're a heartless pig, etc., etc. It's another example that they show. It's not plausible, it's not supported, and of course, it's not true. Right. So in essence, there's a limitation to retrieval. And all this can be just summarized by what I mentioned, that just like a human doing manual research, the model also needs to have that, in a sense, mental acuity, needs to have the understanding of what is realistic. And of course, the wisdom to, determine what is true and what is not. All right. So those are two papers. And there are actually other benefits of retrieval-based models, which we can talk on and on about it. But I want to talk about maybe an application of retrieval-based models. And I also like to bring in a personal example in that it's use cases and applications. One, we talked about retrieval-based LMs can be smaller in model, a smaller size, less parameters, and also it can pull out real-time, truthful, supported information. And the best use case I can think of in this case is chatbots. So I used to work in a robotics lab, and my colleagues work on chatbotting. And like 3 years ago, 4 years ago, it's quite bad. It can give you some answers, but those are generally memorized answers. But I thought that if you could put a retrieval-based LM, which is small, it can be put into something like an NVIDIA AGX Xavier or like a TX2, which can be mounted onto a robot, and it can run that chatbot functionalities. And that would be very good in that domain of robotics. And of course, there are other use case and applications which are still being researched, and there are a lot of works in progress. But that is all I have for you today. And my partners will be talking about the nitty-gritty stuff. So the next we have token level retrieval, followed by passage level retrieval, multimodal retrieval, 2 training methods, and of course, retrieve in context. So thank you, everybody. And yeah, I hope I can answer your question.
I can ask a question.
Yeah.
Cool. So my question is that, is it true that the following statement that the answer must come from the passage you retrieve, or it can generate other things upon the passage you retrieve?
The answer,
like for example, say you're performing a QA task, then the answer, it must come from the passage you retrieved, or it can also be something else, not in the immediate passage you retrieved, but something based on that.
oh, okay.
I think that depends on the language model.
I get what you mean, but I think, yeah, it depends on how they apply it. So in most of what I've read is the model that generates an answer, and then they use retrieval augmentation to go and fetch sources to actually try and back up that claim. And then based on human ratings, they will give you, the top rated answer. So I guess it can also, it doesn't have to depend solely on that one source.
Yeah. So the underlying reason for asking this question is that, I think there is a difference from, like, you talk about the parametric knowledge included in a language model and the actual contextual knowledge, but we're not clear when you're doing the inference, is it actually using the new context or still based on some memorized parameters? So
Okay, I currently cannot answer that question directly.
Yeah.
But I've read something on actually retrieval-based LMs can actually update the information that they already know.
Oh.
So in the sense that whether they are using knowledge already stored in the LM or whether they are using knowledge taken from somewhere, that I'm not too sure. But there are works that, because traditional LMs are known to be not adaptive over time, and they maybe can store static, outdated information. But retrieval can actually help to update those information instead in their parameters without retraining or fine-tuning. And I think I remember the paper. I can link it to you later on, but I cannot answer that question directly. Yeah.
thank you, Alson.
Yeah, thank you.
Other questions? So I guess Yisang's question was in the 70% that Alson can answer, so he didn't refuse to answer it. So very good.
I have the threshold for I don't know.
Great. Okay. Thank you, Alson.
Thank you. This doesn't work.
Can I take my laptop?
Oh,
Yeah.
the laptop there. Yeah, you can use that. Okay, thank you.
Okay, here, my name is Qijiong, and I'll introduce the token level retrieval-based language model. And token level retrieval-based language model is the initial exploration on the retrieval-based language model. So basically, the general language model calculates the next token probability distribution over a static token embeddings. And the token level retrieval language model retrieve extra candidates tokens from memory to optimize the above distribution. They calculate the next token probability distribution by comparing the encoder outputs against the static token embeddings and the memory representations. So what is the memory? The memory is constructed in the form of context target pairs, or we can say key value pairs based on the current training corpus. Here's an example. So on the left are the training contexts and targets are in the middle. So each target is a token, and that is what we would like to retrieve. And these tokens are all in the language model vocabularies. So for example, the sentence, Obama is a native of Hawaii. For this sentence, it has 6 tokens. So we can select the first 5 tokens as the context and the last token as target. And here we also have a context encoder to fuse the sequential context into a unified representations. And it will be used in further distance calculation. Okay, so here is the token level retrieval LM pipeline. First is the memory construction. And during the next token prediction, we'll first get the output embedding. So as the general language model, which calculates the distribution over static token embeddings, here we add another calculation to calculate the distribution over the memory. And after that, we can combine these 2 distributions to get to the final one. So how can we combine the memory with the language model? Here are 2 paradigms. The first one is a decoupled design of the memory with language model. And this work is studied by Stanford. And the other one is to joint train the language model with the memory or the context encoder, which is done by Princeton. The first paper, the generalization through memorization, or we can name it the KNLM. Here's the entire architecture, and the memory part I have displayed in the previous slides. So here, given a test context, the Obama's birthplace is, and the language model will predict the next item. So for the general language model, they'll firstly obtain the context representation. And based on this representation, they'll do the classification to calculate the distribution probability over the entire vocabularies. And here we can see the token Hawaii and another token Illinois has a very similar score that we can hardly distinguish these 2 candidates. So we can leverage the memories here top. Firstly, we can calculate the distance between the current context representations with the entire memory representations. And we can select the top k nearest candidates. After that, we can normalize it. And if some candidates overlap, we can aggregate these candidates. Here, the aggregation part is the final distribution of the memory part. So last, we can combine these 2 distributions to get to the final answer. And we can see the Hawaii, the score of Hawaii is much larger than other candidates. So basically, the probability distribution of KNLM has 2 components. One is the original language model distribution, and the other one is memory distribution. So to conclude, the KNLM makes an initial attempt for retrieval-based language model, and it is only used during the testing or inference phase. That both the context encoder and the language model are not are trained separately. But here comes a shortback. that the memory retrieval is extremely computational expensive. So what lead to such computational expensive? The answer is the memory construction. So here is an example. A sentence maybe have 6 tokens. Obama is a native of Hawaii. So during a memory construction, we'll get 5 context target pairs for this single sentence. That they are constructed in a autoregressive way. So the memory size is approximately equal to the number of tokens of the training corpus. It would be very large. So the sandpaper can reduce such a memory, can reduce such a large-scale memory problem. And this work is produced by the Princeton University. The title is Training Language Models with Memory Augmentation. So we can first think deep with the token level memory. What is the token level memory? So here, the Obama is a native of something. When we want to predict the next item, what we want is the memory is a set of candidates. We hope the next token to appear in the memory targets. So in this paper, they filter the memory first and reduce the searching space. Here are 3 batching paradigms. The first one is very original one, that each samples inside a batch has no relation because the samples are randomly sampled, and we name it default batching. So here we cannot use any other samples from the same batch for the memory construction. And the other one is the batch with the consecutive segments. That means maybe some samples may construct a document and they put one document in one batch. So the samples or the sentence in the same documents may provide some useful knowledge to current token prediction, but the samples from other documents may also not relevant to current tokens. So the next paradigm is to batch lexically similar segments. That they firstly use BM25 algorithm to select the most relevant samples for current sample. And they hope other documents or other samples may help that they may have some candidate answers to the current tokens. So here the memory is not constructed by the entire training corpus, but constructed by the current batch. So the retrieve candidates from in-batch memory, but not the entire corpus. There are 2 steps to construct the in-batch memories. The first step is to use BM25 to select top K relevant samples. And then we can produce context target pairs for each sample inside the batch. And here K is much more smaller than the number of sentences in the entire training corpus. So the memory would be reduced extremely. And they use 2 distributions to calculate the training objective. The first term is the original language model distribution, and the other one is the memory distribution inside a batch. So based on the third batching paradigm, when they encode a context, the jobs become CEO of, and the next token representation can be retrieved not only by the entire token embeddings, but also from in-batch memories. And here comes the answer echo. So here they have three types of memories. The first one is a local memory, that the memory is only constructed by a single sample. And the long memory is what is the memory constructed by the in-batch samples. And also have external memory that is the original one, that the memory is constructed by the entire training corpus. So in the experiment, they will compare these three types of memories. Okay, first, we can look at the purple box, that both the local and long-term memories can boost the performance of the original baseline here. And second one, when they use the external knowledge, external memory, they will get a better performance compared with the long-term memory. But if only use the external memory, but without the long-term memory, the performance will also reduce. So in this experiment, the long-term memory can be verified with its efficiency and effectiveness. Okay, here is the efficiency, that if we use actual training corpus memory, the inference speed will be very slow, like 300 times per second. But if we use the long-term memory here, the training speed would be 10 times faster than the original one, than using the external knowledge. Okay, to conclude, this paper incorporates the retrieval into the training objective, and they verify the long-term memory will gain both efficiency and effectiveness. Okay, thanks. Next are two papers I would like to share today.
Any quick questions?
Yeah. Okay.
Like some of the following the literature for it is really impressive that BM25, despite it's been around for decades, and there are so many new embedding models out there that time and time again people still fall back to BM25. And today this is like the second time we've seen it come up, and I also read other papers, and yeah, it seems like something that has withstood the test of time. Why do you think that is so? Especially in the modern age, there are so many types of embeddings out there for retrieval.
So here they use the BM25. What I think is that the BM25 is a large filtering for the entire corpus, and during the training, they'll rank the candidates inside the batch. So that is a two-stage filtering. The first stage is use a simple BM25 to get all the possible candidates inside the batch, and then during training they'll use some precise supervision objectives to tune to search for the local batch candidates.
I think you are saying specifically for this data set, but I think maybe more like in general, why is BM25 still popular compared to other models?
I'm not sure why it's popular. But one of the possible answers is that BM25 is an efficient way to get the most relevant candidates, and maybe compared with other algorithms, it's simple and efficient.
Yeah, so the other answer is you should take our CS3245 course. Take our undergrad IR course. So I mean, I used to teach that, and I think Qijiong is very right. BM25 is a very elegant method. It's geometrically inspired. It's darn fast compared to training a model. And it's very replicable. If you look at BM25, it's like cosine similarity, but with length penalties built in. There are a tiny bit of hyperparameters, just 2. So you only need 2 parameters compared to how many billions of parameters you need to set for a neural network. So a lot of times we see BM25 used because exactly as was stated, it is a good baseline model. It's very fast to compute. So most scientists prefer to use BM25 as, if they don't want to pay attention to that part, right? So this is a paper about language models. It's not a paper about retrieval. So they're going to just say, just use the simplest possible tool for IR. So they'll use BM25. It's like you go to your hardware store, you want to buy a hammer, you just buy a ball peen hammer. Who cares what it looks like? You're not going to buy a fancy one that can auto hammer, has battery, has a remote control, all that type of stuff, right? You just want a hammer. So BM25 is the natural IR model that we tend to select for that. Okay.
If I got you correct, it doesn't mean that like token level retrieval don't really have a lot of applications in, right? So what are like the modern use cases? Is it just like training your LLMs, or what are the modern use cases? Yeah.
So, sorry?
What are the modern use cases for
The modern use case,
the
I'm not sure. I'm not sure yet. Because after the large language model appears, I think such token level retrieval has little use. Yeah.
Wait, thank you.
Okay. Thanks.
Okay, so since the previous QA was talking about retrieval, the next part will just be about retrieval. And you will see a lot of retrieval methods, and I will introduce what is retrieval. So, of course, retrieval is a key part of retrieval augmented language model. And this is a typical use case of retrieval when we use our search engines, or when we find an FAQ, for example. The user types the question and we retrieve from a corpus. This corpus may be consistent of millions of documents, or it can be from Wikipedia. And then the goal of retrieval is to retrieve a list of relevant documents. And what we mean by relevant is defined by ourselves. So in the case of question answering, usually the meaning of relevant is that the document should contain the ground truth answer. So this is, for example, if you ask a very hard science question, then through retrieval, we hope to retrieve the document, and we actually use it every day. And yeah, so I'm going to talk about BM25 later. And before BM25, let's look at TF-IDF. So I'm not sure how many of you have heard about TF-IDF before. Right, yeah, I think many of you, right? So this is probably one of the most important concepts in NLP in general. So the TF-IDF is to give a score to a term within a document. So there are two components. One is called TF, is term frequency. It just counts how many times the term occurs in a document. And the other is the inverse document frequency. So this is more difficult to understand, but it's also quite simple. It's just the log of the inverse document frequency. So what do you mean by document frequency? It's the number of documents containing the terms divided by the total number of documents. So why do we need this term here? So as you can imagine, some terms are just too common to be truly meaningful. For example, there are terms like the, and, right? It occurs in every document in your corpus. So in this case, we will use the inverse to show that those terms that occur in every document are not useful. So if you say, for example, this is 1, right? Then the log of 1 is 0. So the term is just ignored. And this is the TF-IDF. And this is a more concrete example. So yeah, I can just briefly talk about it. So for example, if we only have 3 documents, this is good, this is bad, awesome, this is awesome. Then as I said, we will have 2 parts. One is called term frequency, where we calculate the frequency of a word in the document. So for example, in sentence 1, each one will just have 1/3. And the other set is called the inverse document frequency, which is the inverse of the document, the log of the inverse of the document frequency. And like I said, those terms that are very common will be given a weight of 0. So in the case here, we see that the word this and is occurs in every single document. So it doesn't help us to distinguish one document from another. So we consider it as meaningless and we just ignore it. And finally, we will have a set of feature vectors. And we call these sparse vectors because obviously most of the terms have an entry of value of 0 because let's say we have around maybe 50,000 vocabulary, and one sentence maybe just containing like 10 or 20 words. So most of the words doesn't appear in a sentence. That's why for these vectors, most of the entries will be 0. And that's about TF-IDF. So next we are going to go into BM25. Right. So BM25, what does BM mean? Anyone can guess? BM? What is BM? Right. Very simple. I mean, yeah, no, it just means best matching, right? Just best matching. Yeah. And so there's this formula here, and if you look at it carefully, we can see that there is this IDF still occurring here. So so it's based on TF-IDF, but it's modified. So the IDF is still here. Then what are the rest of the formula doing? And we can take a look. So for the blue part, this is the F, Q, I, and D. It's the term frequency. It counts the number of times it occurs in a document. And why do we put it in both the numerator and the denominator? Is that we want to avoid having this term to be too frequent and then causing the entire thing to just go up. So so for example, if you imagine if we have a document that repeats the same word for 100 times, then this term frequency will be very large, right? Because it's just 100. But we don't want to do that because it's not meaningful as well. So the authors propose a way to mitigate this. Is called term frequency saturation. It means that when we add this into both the numerator and the denominator, then eventually the score will just reach 1. It doesn't go up infinitely, which is what we want, because if it repeats too many times, it's not meaningful. And the other side is that we put this term here to penalize the long documents. So this is also intuitive because we look at here. So we have this D. This D is the length of the current document, and divided by the average length of all documents. So if this whole thing is large, meaning that the document is very long, it means that the denominator will be very large, so the score will go down. So this is also intuitive because we understand that if a document is very long, then it can contain many terms, and some terms can appear multiple times. So naturally, TF-IDF favors long documents, and we put this penalization term here. And so overall, we can see that, like what Prof just said, there are two two parameters to be tuned, just two, the K1 and the B here. So all you need to do is to figure out what are these two terms. And I think empirically they give some values to that. Yeah. And so during the real search, what people will do is that we have a query, right? The query may have I think n tokens and words, and then we will score this. So the score for the query with the document is given by the sum of the individual scores of each token, and then that's our key. That's the key motivation of BM25. Yeah. So okay, yeah. So that's the most classical method of doing retrieval, and you have seen it previously, and you will see it in the later papers where people still apply today. And yeah, so I will compare it the different methods at the end. But let's go into the modern, like more modern way of doing passage retrieval. And in this field, the most classical task, although it was just published in 2019, but it's still considered already considered a very old paper in dense retrieval, is called dense passage retrieval. Yeah, it's just very simple name. And the structure is also quite intuitive. Is that we hope to encode the questions and the documents into vectors and use vector similarity search to do retrieval. And so here is an example. For example, if we ask who was the inventor of the compiler, and we have a set of documents, and each of them will go through an encoder, and we produce a vector. So and to measure the similarity, we just use the dot product or percent similarity. And in the actual implementation, the authors used BERT because this was the most popular method back then. And after this work, there are other ways of applying the same dual encoder structure. For example, people can use T5, which are larger, and more recently, people can even use Llama to train a dual encoder model. So, but they all fall back to the same paradigm of using two encoders to encode the passage and the question separately. And so how do we train this encoder? We know that we have a set of questions and a set of documents, right? So how do we make it model work? So this is the most important loss in dense retrieval, is that the contrastive loss, which means that given a question, we need to find just one positive document, and this positive document is just content. Well, we hope that it contains a ground-truth answer. So that's the positive document, and we have a bunch of irrelevant documents. So it can be randomly chosen, or it can be mined. For example, maybe some articles are quite similar, but they actually do not contain an answer. So we can put them as hard negatives. And the overall goal of the training is to maximize the score of the score between the question and the positive document, while minimizing the score between the question and the negative document. So it's also quite intuitive. And so this is the figure of the DPR from the DPR paper, and some concepts here. So the top K accuracy refers to the number of retrieved passages, because when we do retrieval, I mean, we for example, we retrieve from a corpus made up with 10,000 documents, then we can use all of them, right? But usually people just use top 5 or 20. So the K is the number of retrieved passages, and the top accuracy is measures whether the document contains the real answer. And we can see that intuitively, the number of when we increase K, we have more documents. so it's more likely to contain the ground truth answer. The performance goes up, but of course there's a little, past a certain point, then the retrieval quality of the documents decrease. So we don't see a linear increase. And you can also see that with some training, and the DPR model is able to outperform the BM25. So the blue line here is the BM25. And with just 1,000 training examples, it's able to outperform it. And when we use more training examples to better train our encoders, then they are able to increase in their performance and finally reach a very high score compared to the BM25.
There's a question.
Yeah.
The K, the y-axis K, the x-axis K, and the legend K, are they the same K?
No. So
What is what?
It's
Thousands, right? So in the x-axis, it's not 100,000, is it?
No, it's not. This is a number of retrieved passages. So here the K is 1,000, right? 1,000 examples.
Okay.
This is the number of retrieved passages.
And then what is the top K accuracy?
Oh, how do I put it? So for example, when we have 20 retrieved passages, then we measure the top 20 accuracy. Because
But if you only have 20 retrieved passages, then why is there a top 20? Shouldn't it just be 20?
So the top 20, we have 20 passages, right? They may or may not contain the answer. So if they contain the answer, we will classify, consider it as a 1. The other case
So
0.
what I'm saying is, why is there the word top? If there are only 20 passages, then the top 20 is also the bottom 20.
Okay.
Yeah.
So you say there's like K's a number of retrieved passages, and then you take the top K passages.
You have 100 and then you select. That's one.
So this K is what?
What was the x-axis K?
Yeah. Which
Is it like
do we have 3 different Ks here, or only 2 different Ks?
There's this case 1,000.
Right?
Okay.
Okay, so the K in the X and the K in the Y, is it the same K?
It's the same case.
Then why is there a top?
So when we actually implement, for example, if you actually use this algorithm, it's you don't actually set a threshold. You obtain a sorted list of the documents, and you just cut off. Like if you have let's say 10,000 documents, right? When you do retrieval, you have it will return you a list of 10,000 documents, but it's sorted based on their score.
Yes.
And then you take the first, which means the top K.
Okay, so what you're saying is that you retrieve 100 passages and you consider the top 100, but actually you are retrieving more than 100.
I think can I try to rephrase this answer? Okay,
Mm-hmm.
when we say top K accuracy, it's just a name. Okay,
Yes.
so okay, when you see the x-axis, what we really do is so that there's one the ground truth answer, right?
Yes.
So the x-axis K is how many chances do we give? So like for example, let's say it's 20, we retrieve the top 20 scoring. So as long as in the so it's like 20 chance. So inside the top 20, as long as there's the right answer is in there, you count as correct. So that's why in the x-axis, as long as they increase.
So this accuracy is not number of documents in the retrieved passages, but it's the number of iterations that you try to retrieve that number.
No, you do retrieve like say 20 or 40, 60, 80, 100 out of like a big pool of 59,000.
Yes.
Yeah, but we just give this number called top K. It's a naming convention.
Yes.
Yeah, but effectively what I mean is how many chances, as in
let me rephrase. So is this top K accuracy the number of correct passages in the retrieved passages?
No, the number of chances.
Number of
things you pull
number
out.
of batches that you pull out from the
Number of documents you pull out, and then from there, what is the
If any of them contain the answer, then it will be considered correct.
So can I try to visualize it? So like the K and the x-axis, that's how many passages we retrieve.
per batch. something like that.
Let's say like 20 means retrieve 20 passages from the 10,000, the list of 10,000 passages, right?
Yes, that's my understanding of it also.
Then top K accuracy means that you can randomly sample any 20
yeah, that's right.
from the entire
So the
list.
number of batches.
Then the top 20 means that you take the best 20 scores and then you agree with that.
Okay, no, because my interpretation of what they're trying to say is you have 10,000 passages.
Yeah.
Each time you pull out 20 of them.
Okay.
And then if in one of these 20 there's a correct document, then that batch is taken as accurate.
Yeah.
Then you repeat this iteration, you pull out many sets of 20, and then the percentage of batches of 20 that are correct will make your top K accuracy. Is that what you're trying to say?
That's right, that's right.
Okay.
Okay, so to rephrase, let's say your test set has 10 questions. The test set has 10 questions. Your full data set is 59K and 59,000. Your full data set is 9,000. And you select your x-axis K to be 100. So that means, let's say for question 1, you pull the top 100, and in the top 100, that is the ground truth there. So okay, that's correct. So that's like one point. And you keep doing that for the 10 test set. And the accuracy is like
this doesn't show what is the sampling amount for the top K accuracy. You only know the batch. You only know the batch size, but you don't know the number of batches used to estimate the accuracy.
As in the number of batches is basically your test set, like how many
Questions you have.
Yeah, in this single test.
I see. Okay. Yeah. That's fair. But that means that you will get a saturation, right? Like if you retrieve 20 at a time, if only one retrieval out of the 20 is correct, versus all 20 are correct, then there's no difference in the score.
I believe in this example, there's only one ground truth. As in like out
Oh, I
of
see.
all 59 days,
Fair.
only one is correct.
Okay,
Yeah.
okay.
I believe that's the setting. Right? Am I right?
Yeah.
Yeah. So yeah.
So I posted the original paper and the caption for this slide in the channel, the general channel. You can take a look at the actual paper and try to make sense of that. We have this established that the x-axis is the number of retrieve passages from the entire corpus, right? So you can, just like you ask Google, you can look at just the first result, or you can look at the first 20 or the first 100, and you can see how the curve generally increases, right? So you retrieve more results, there's more chances that some number of documents will be relevant, okay? So that's one way to look at it. The x-axis, they maybe Tongyao can describe, I'm not that very clear about it. When they say top K accuracy, it's not necessarily over the same K passages, is that right?
I think so for example, we have a corpus, right? This corpus has 10,000 documents, and when we do retrieval, actually it gives a score, right? So previously we mentioned that the dual encoder gives a score. So it gives a score to all of the 10,000 documents.
Right.
And we can sort this, right? So we can find the most the documents with the highest score. And from this very long list of 10,000 documents, and we can take the top 100, for example. And if any of these documents contain the answer, then it's considered a true, like successful retrieval. Otherwise, it's failed, and the accuracy is just measure the kind of success rate of the retrieval.
So basically, when they say like there's 90% accuracy, so 9 out of 10 of those documents that we expect are accurate in that 100 that we retrieve, right?
No, the accuracy is measured based on the test set, which is a question. It means that it means that, for example, we have 100 questions and your accuracy is 19%. It means that 90 of your questions, you are able to get one document in your top 100 that contains the answer.
So actually,
I think what you say is that we don't need a 2D graph to show the, let's say, top K% accuracy.
Oh, yeah.
So actually, if you don't understand this graph, that means the author is making something that's that's a detour. So actually, you just need a 1D graph or 1D table to show all the results. If they mention top K accuracy, then you don't have to say, okay, K is the number of retrieval passages. Actually, you just mention it's top K. Yeah, you just mention it's top 20 accuracy, then it's okay. You don't care about how many you use.
Right. I think here they put it
So usually I see people report the top K or something at K just in table, not in the graph. Otherwise, they will compare something different, not compared to the number of retrieval passages.
I guess because usually when you're using it as a metric for your own model, you don't really have to care so much about what the K is. Just pick one.
Yeah. So, but I want to clarify that. So the K here in retrieval is important because of the application of retrieval system. Let's say if you are building a Google, right? Then your first page maybe only can show 5 results. Then in this case, you are concerned about the top 5 accuracy, right? Because I mean, very seldom you will go to the second page of your Google search. And in the same case of retrieval augmented models, the models have a limited context length, meaning that you cannot put all your 100 documents in the model, and it will be definitely slower than, let's say, if you put 5 documents. So in this case, researchers are usually concerned about the K because it just gives you a measure of how good your retrieval system is. And of course, you can imagine if we just use let's say top 10,000 passages, then everyone just be very happy, right? Because much content answer, but this is not goal of the retrieval. The retrieval is that we want to make the documents that contain the real answer to go top in your list. Yeah.
Everyone clear about that? If you retrieve too many documents, then you have to do another retrieval on top of the corpus that you just retrieved. So it doesn't help, right? So you need to make sure that your retrieval is at the right size. Like Tongyao said, if you're trying to retrieve a top K of 5, that means you want the top 5 results to show a good answer.
I suppose in some cases it would be useful to use a fast model to do a quick retrieval, and then use a slow model to do a more fine-tuned retrieval from your first retrieval, and then finally use that result.
Yeah, there are lots of staged retrieval models that you can use. Yeah. If you have easy problems that you can solve using a very simple method, you use that. You scaffold the harder problems using more computationally expensive methods.
Yeah. So, but by the way, the key idea of this figure is to show that the number of training instances matters. So their definition of the training instance is the number of questions with annotated passages. So meaning that this is from natural questions. So there are 59,000 questions, and the annotators label for each question where does the answer come from a Wikipedia document. And so a natural wonder for us is that, so what if we don't have any training data? For example, in many customized settings, let's say you have a in-house document store, and there's no way for you to annotate a large number of questions and document pairs. How do you do that? So a more recent work is called Contriver, and the name is unsupervised dense information retrieval with contrastive learning. So I think all of these terms you have seen them before. So the dense information retrieval with contrastive learning, the previous laws I just introduced, and their main idea is we want to do it in an unsupervised way. And since we are in an unsupervised world, so there's no label or anything. We have to make our own instances. And here the author's main contribution is that they find ways to create positive instances from an unlabeled corpus. So anyone of you think why positive instances is our focus, not the negative ones?
Because your end results trying to find accurate like documents that you can use as context, right? So you find the positive ones.
Yeah, kind of. So remember that definition of the negative pairs is that the query is not related to the document, right? And in an unlabeled corpus, when we do a random sampling, then very likely they are just unrelated, right? So it's very easy to find unrelated query and document pairs, but very hard to obtain, especially the golden set of positive instances. And they use two tasks, mainly the inverse close task. So the idea of the close task is to fill in the blank, right? But the inverse close task is that given a query, which is just a span of a passage, we want to be able to retrieve the remaining tokens of the document. This is to enforce the model to learn that, okay, given a span, I want to retrieve the other tokens. So to learn their kind of dependency. And the other is called independent cropping, and it's similar to the close task, but it's more brute force. So given a span of a passage, we want to retrieve another span of the passage. So another span of the same passage. So these are the two ways of creating the positive instances. And after you have positive instances, and you can just chain it like a contrastive loss, and the negative instances can just be randomly chosen. For example, so we have a positive instance from the same passage, and then we choose another document from another passage that will be a negative instance. So this is the result for the contriever model it looks okay, in blue there. So their main conclusion is that, yay, we get some model that is on par with BM25 for unsupervised retrieval. And this shows how strong BM25 is when there's no label. So like previously, when we talk about BM25, we never say anything about the training, right? But here, contriever is able to achieve that for most of the question answering data sets. But of course, we can look at the left part here. So the PM25 is very, very good at these two data sets, while the contriever, although it's very strong on other models, still underperforms. So also explains why. So we look at these two data sets. The first is check COVID data set. So this is about COVID questions. But unfortunately, the contriever, when it was doing pre-training, it doesn't have information about what happened after 2020. So it doesn't adapt to this domain. Therefore, it fails very sadly. And the second data set is called Torch 2020. And this data set contains long documents, meaning that these documents may be around 2,000 tokens. And usually, because we are using models, we are using encoders, transformers encoders to do document encoding. They have a limited max length, maybe 512 or 1024. So when we have a long document, usually we will be truncated, and this explains why it's bad for the. It's always a hard problem for dense retrievers, whereas for BM25 it's quite robust. So among all the data sets, you can see that it performs quite good, and yeah, that's the key idea of contriever. So finally,
can we go back to that slide? So I just want to point out here, BM25 is doing some cheating. Okay, why is that? Because when we think about BM25, it does get some statistics. It gets IDF statistics over the entire data set. That means for Track COVID and Touche 2020, right? These two data sets, it actually has IDF statistics. IDF statistics are drawn from the entire data set, right? So that's why it can do well. If you used, for example, all the other corpora like NF corpus all the way down to Quora, you use that to compute IDF statistics, and you try to test it on Track COVID, it would not do well. Why? Because we know the Track COVID results have a lot of instances of COVID-related data. And so the IDF for COVID-related terms would be completely off. if you had used the other corpora to do that. So the same problem as they're illustrating with any type of trained DPR system, dense or otherwise, would still happen with BM25. Okay, it's just that BM25, we're not actually training on the documents, we're just training on the, well, not even training, we're just compiling statistics about the corpus itself at the token level.
Way is it saying that if you fine-tune the model or the data set, the performance will be much higher?
Yes.
Yes, so if you check the original contributor paper, if you fine-tune maybe on around 1,000 examples of any of the data sets, then you will go up immediately. That's the power of the models learning. Yeah.
So this is an important point for anyone to remember, is that when you talk about even TF, IDF, or BM25, they're still using statistical data over the entire corpus. We never in IR split the statistical data of a corpus between testing and training for doing most of our experiments. Okay, many times we are not looking at that as a scientific question, so we don't separate that. But in certain cases we do. So when we're doing information retrieval experiments and there's a training and testing corpus, then we have to separate out statistical data for both. Okay, so that's why if you think about it, there are lots of times when we do retrieval using a BM25 or TF-IDF that doesn't work very well. And that's because there's a mismatch of the corpus. On the web, the 20th most common token on the entire web in English is the word copyright. Okay, you know why that is, but that's not true of normal English data. Okay, normal English, we hardly ever use the word copyright, but we know why it's very common on the web. Okay, so our IDF statistics are wrong. Okay, because we're not matching. Okay, just to make that point.
Then like training like a BM25 on like a larger data set really help, like see the power of a very large data set.
So that's why you always, a lot of times you want to get an IDF from a representative corpus, right? It's sort of like the training and testing separation. In machine learning, you always say when you learn a model, it has to be on the data distribution of your testing set. Otherwise, you're learning a model for one thing and you're testing it on another, which is exactly what happened here, right? Contriver was trained on some stuff, but it never saw anything from 2019 onwards. So it cannot do well on that because the training was not on data that is being tested on.
Right. So the final part of the more advanced version of dense retrieval, I'm not sure if you have a previous wonder, like why we squeeze everything into a fixed dimension vector of 768, right? So the authors it's also concerned about that. So there are ways to do multi-vectors, to have multiple vectors for query and document, and Cobalt is the most classical work of doing that. So remember that we have a question encoder and document encoder, right? And when we pass this through the BERT, it actually gives us an embedding or a representation of each token for the query and for the document. So what the authors do is that instead of just using the one token, one hidden state as the representation of the entire query or the entire document, they will actually use each individual token from the query as well as the individual tokens from the document and compute a score and take the max. So for each query embedding, they will go through each document token embedding and take the score with the maximum value, and finally have a sum of the score. And so one issue, which is very obvious with this method, anyone can think of? Like think about how in our real application, when we want to apply this to build a product with a lot of documents, millions of documents. Right, exactly. So remember that previously, if we only have one vector, then we just calculate the similarity once, right? But here we have a lot of vectors. So the query maybe have 20 vectors, then the document have 100 vectors. Then when we use this maxim operation, it's very expensive. So 20 times 100 for just one query, right? And our corpus is very large, so this will be quite slow. And so in our original paper, the authors proposed different optimization methods. So covert to this day is still the most, I would say, most popular way of doing re-ranking, meaning that like what Nicholas just said. So when we will use a simple retriever, for example, BM25 or DPR, and we obtain a set of, for example, top 100 documents, and we will use more fine-tuned models, more fine-grained models like covert to re-rank the documents. And this usually improves the score because it has more information about the query and the context and models their interaction better. So to summarize, here's a summary for the sparse retrieval. So the advantage of sparse retrieval is that it's typically faster and it's more efficient in storage because most of the entries are just zero. So you don't need to store the empty ones. You just need to store those with a non-zero value. And it gives you very good baseline performance. There's no need to fine tune, you just apply it. You have some statistics and you just apply it. And also it gives you an exact match of the terms. So it's quite interpretable, meaning that because we are using term-based weighting and scoring, right? So we know which term gets highlighted. So for example, if I'm searching about Mac OS, which version, Big Sur, then I know that, okay, maybe the Big Sur is the keyword and Mac OS are also the keyword. So we know which term gets weighted higher and it's quite interpretable. However, the bad part about it is that first it's quite hard to improve, which is also why to this day people still use the BM25 classical system because it's quite hard to improve on this. And there's a big issue with the vocabulary mismatch, meaning that if we want to search, let's say I'm going start of COM3 or beginning of COM3, then you cannot do it because I mean the vocabulary doesn't match each other. And of course, you can think of ways to use, for example, synonym dictionaries to do the augmentation or expansion and all that, but it's just doesn't go with today's trend of using large models or language models in general to capture the similarity of the semantics. And on the other hand, for dense retrieval, there are many pros. Of course, it outperforms sparse model with fine-tuning. So as long as you have some training data, you can train the dense model. And it can search with human-like concepts, meaning that it does not rely on the terms, but just on the overall semantics of your queries. And it also enables multimodal search and cross-modal search, right? So let's say if you want to search an image based on your text, then you can't do it with BM25, right? Because BM25, you have to have the tokens and terms. But here you can, if everything is a vector, then you can easily look out for other modalities also represented in dense vectors. And that's its flexibility. And that's why in many like cross-model vision language models, if they want to do retrieval, usually it's dense. And on the other hand, the cons is that it requires training data to work well, like the previous DPR figure. More training data gives it better performance. And it does not always generalize very well. So particularly for a very niche terminology. So this is like what we saw earlier about COVID. So if in your training data, your COVID word just appears very few times, then it just doesn't generalize to this kind of terminology set. And there's more compute and more memory for sure, because we are using a model. And the model, when the size is larger, it's better, but there's much more compute. And we have to store a dense vector for all the documents, and it's quite expensive. And also during the actual search time, we need to search calculate the dot product between one query and maybe 8 million documents. This will be quite slow. And there are many libraries to optimize that. And it's not using exact match. So meaning that if you want to have a word that contains exactly the word apple, then you cannot get it because it's just dense retrieval. There's no way to interpret these embeddings, so it's not easily interpretable. And that's the cons of dense retrieval. But to this day, usually dense retrievals are more powerful. But like what you just said, although they are powerful, they are not widely applied. So sparse retrieval is still a very strong baseline if you just want to use retrieval as a small component of your entire pipeline. And yeah, that's all for my part.
Okay, in the interest of time, let's go directly to the next presenter. I know Hengchang was watching his watch.
Yeah, I will control my time. Yeah. I mean to.
We need to refresh.
Yeah, because I made some edits.
Yeah.
Yeah, thanks to Tongyao, that's clarify many concepts. I will also like introduce next. But let's think about if we retrieve some text, let's say documents. So next steps is how to like use this retrieved one like in the language model. So this is what here I would like to introduce. So I will give a background first. So starting from a work proposed in 2020. So it introduced a way to like doing a pre-training language model, but this one actually is used for the downstream QA task, like by tuning it. But anyway, I will introduce the pre-training stage first. So in this work, it introduced that if we retrieve some like relevant documents, and currently I want to do a masked language model pre-training. So what I want to do is like to use this retrieve the text, like just put it into the original inputs, and then hope it can make the correct prediction like in the mask position. So how it do it propose like two stages. One is the retrieve stage and another is read stage. So retrieve stage is just retrieve. Like actually it's pretty simple and very straightforward. It's encode the documents and the input separately by like share the encoder actually. And then like use a neighborhood search algorithm to find the most close one, and then like retrieve the top view and for the downstream read stage. So the read stage is actually I actually not quite get why it's called read stage, but anyway, just called so. So the read stage is like if I retrieve like 10 documents, like which is in the neighborhoods, and then I like do some average weighting, like based on this all the retrieve the inputs, and then actually the weighted average here it means like whether the document is retrieved one or not, and then I will average them all, like given the final distribution of the text prediction. So this is background. So now I would like to introduce two works, which is I think is very new. It's one published in the May 2023, and another is published in August. So the first one is also follow the paradigm of the one I mentioned in the last slide, and another one is introduce a new paradigm like using the Retrieval-in-context LM. So I will introduce the first one. The first one is called RALM. I will just brief it as RAL. So let's take an example. So the X is like World Cup in 2020 was blah 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 blah. Before it's increased to then is the text I want LM to generate. So in this case, for the text generation, actually it face some. It's quite similar to the pre-trained masked pre-trained language model, but actually also kind of different because the Y have many words. So which means like in this case, we need to, it predicts like many Y, like in different position one by one. So actually, firstly, this work proves that put the retrieved document in the context actually help. And like you can see that with the actually the Y is perplexity, which means lower is better. And within the smaller size model, it actually like improve more like with the retrieved documents, which is like kind of aligned with our intuitive because like small model do not have that many knowledge. So probably the retrieved documents can help that. And also in this work, it's this is quite actually many maths here, but actually it's quite simple. So the first math is that in the standard language model, it just predicts the words one by one. So that's it. That's all. That's the concept. And the second equation shows that in the retrieve augmented language model, the prediction of next word is not only based on all the previous words, but it's also based on another part is based on the retrieved text. So it's actually based on rely on two sources of information. One is the past text and another is the retrieved text. So this is the second equation. And this realm, this work proposed that actually there are some problems because you need to generate the word one by one, which means that the efficiency is quite low. Because every time you need to retrieve something and every time you need to generate something, which is like, it's not quite ideal for the text generation. So it proposed two strategy. So the first one is called retrieval strikes. So I also show a case example here. So for example, let's say the input is World Cup 2020 was last week's what? And if we just retrieve one times and retrieve the text in the pink color, we probably cannot get the correct answer because the team of 40 in the 2026 is not in the retrieved document. So we need to retrieve it more frequently, but like how frequent it should be. So another case is that if we retrieve the information like from two times, like the first time we can get that okay, I can get the intermediate answer that with last with 32 teams before the increase, and then we put it into the input again and retrieve another time, and then we can get like the further more details, like the following words can be like 248 to blah 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 blah. So then this is retrieved two times, can think that it can match the correct answer we want. So the first findings that this paper provides that is that actually retrieving more frequent actually help. So like the one is like retrieve the word one by one, but actually it also means that it's like sometimes because the inference time is more and more, so it's kind of balanced. So if retrieved more frequently, the performance actually get better, but the inference time is actually like blown, that's like increase a lot. So it depends on like the real usage scenario, I think. And yeah, to summary this, so I think there are too many words. I probably just skip this part. So, but anyway, this part is actually basic, the same like what I have mentioned above. That is well retrieve the documents like in multi-steps, but instead of like retrieve it just once or like one by one. So it's sometimes like you can find the intermediate optimal like. But also like there is another problem that you can think that if you retrieve the documents one by one and concatenate it to the original input, the input will get longer and longer. So actually in current LM, I think many of language model like can generate very long answer, can generate very long output. So it means that if we send this all output into the retrieval stage, so the complexity also like increase and increase. So this work proposed another solution that is called retrieval query length, which means that we just need some part of the input instead of the all part. Like this is an example. So consider the X is quite long. So there is a quite many information like within X. And so the retrieval cannot find a correct answer, like because there's a lot of noise here. So so it finds like kind of irrelevant information. But if we just use the final few words, like the word cup, like starting from World Cup 2020, and it can retrieve some information related to the World Cup 2020 and so on. So it can retrieve the correct answer. So which means, so probably the last few words just like more important. So this is a more formalized version I write like based on the observation. And in the experiment, it's also provide some analysis based on this one. So the first one is that the shorter part of the input probably can help more. So which means that because the original input is too long, so probably shorter one can provide more information. But there is some kind of threshold. For example, in the 60 is too short. So in this specific task, it said it's too short, so it's even like getting worse. So there is still kind of optimal point that is not too long or not too short. So it's also like aligned to our thought. And also, so for this work, this is the introduction to the first work. So I have some, regarding this work, so we can find that I have some thinking about this work. So firstly, yeah, it still will increase the inference cost because the larger language model occurs and the language model size grows like larger and larger. If you use the retrieval model to like in the language model, we still need to tune the language model because like language model don't know like how to use the retrieved documents like as the context. So the inference cost is still high. And another is that, yeah, because we need to concatenate the retrieved documents into the original input. So probably the original input is like ignored in the following steps. So this is another probably drawback, and probably improvements can be done based on this. Yeah, and here is another like work. So actually this work kind of solves a problem, I think, in the previous work. It proposed that like in the first paradigm, it shows that okay, current LLM need to be tuned, need to be trained like based on the given the retrieved document in the context. It need to be trained to like to use to like learn to how to use this information. And this work proposed another paradigm. It says that the large language model is too large, probably it can over 100 billion or so. So we don't want to train or tune the language model. We don't want to touch it, and we just want to use it as a black box. So we need to train another thing, that is the retriever. So I need to train like I need to want to retriever to retrieve more correct or more relevant information for us that language model just directly using. So this is another like paradigm. So in this work, it's proposed two paradigms. So the first one is the I just freeze the retriever and then use it in the language model. And another one is to train the retriever and use it. So I will introduce it one by one. So the first one is the retriever freeze one. So there are actually 3 steps. So given the input input X. So firstly, it will retrieve the relevant documents here, and then to like the method I mentioned in the previous work, it will concatenate the different D like separately, independently, one by one to the X, and then send them together like into the black box LM, and then they can get the next works probability. And in this case, it's directly add them with some weight. So the weight is the similarity between the documents and the inputs. So as I show here, so it's use the cosine similarity between the ED and EX actually is average representation of the inputs X and all the inputs all the documents. So yeah. So and yeah, so this yeah, as I show here is like a softmax similarity between these two one. So yeah, so this is a retriever first one. And also it provides another version. It's called retriever trainable one. So that is the retrieval is trainable. So the basic idea is that I want to retrieve the thing that should be like generated by the language model. For example, in the previous example I mentioned, so the World Cup team will increase to what? So we want to expect language model to generate like 48 teams, like blah, blah, blah. So we wish retriever just retrieve this information. Like the retriever should contain like, provide the information like the 48 team, like blah, 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 blah. So we want these two information aligned with each other. So this is the basic concept. So that is how they implemented it. So the first one is just calculate the likelihood of predict the whole following sequence like one by one, like using some kind of softmax. And also the language model likelihood is also the same, like similarly. But these two all like both are controlled by a parameter, like to control their, I think it's like softness of their matching. So the matching between these two is just use the KL divergence. So it's quite straightforward. And the result actually like also support their opinion that firstly the two provided which both retrieval frozen one and the retrieval trainable one is better than the original, and the LSI is the trainable one. So the trainable one is much better than the frozen one with larger margin. So you can see the difference, like even like almost 1.5 times or 2 times better. Yeah. And also to avoid, because in this you can find that in previous slides that because this can be seen like in sampling method. So to avoid the improvement is caused by the in-sampling way. So it also like to conduct another comparison, like to compare if we retrieve the document randomly, like the input into a concatenate into the original input and make prediction, to compare it with like other method, like their method. So can see that the randomly is obviously is worse. Of course, this is also the metrics for evaluating the performance. Actually, I don't quite get. I'm not quite familiar with the bits per bytes, and I have done some research on this one. I don't find any clue why the bit per byte can be used for the performance or such thing. But anyway, it uses this one for the performance metrics, and the lower means better. So the random one is the worst, and the trainable one is the better. And yes, yeah. So this also means that the performance is not solely due to the aggregation of different results, but it also means that we should retrieve some like relevant document. Then we can have the downstream like more accurate outcomes. Yeah. So and there is some reflection on the second works by myself. So firstly, yeah, previously I also have some questions that why people like use like BM25 and even the cosine similarity in this work. They are like all very simple methods, but Tongyao partially answered that question, that because we can improve the efficiency. And in many like real world case, we need the efficiency. Yeah, probably this is the correct answer. But even though they are both too old school, so probably we need some like better algorithm in the retrieval algorithm probably. And also in this work in the retrieval, they just tune the text encoder. So this is the only part with the parameter in the retrieval. So probably there are some thinking about like where else we can tune, like what kind of other parameter we can put in the retrieval, like can be tuned for further like improve the retrieval accuracy. Yeah, so that's my part about how to put the retrieval into the context. And the next part I think is multimodal retrieval.
Hey guys, so today I'm going to talk about multimodal retrieval. It's mostly going to be about on Meta's image bind paper. So very briefly, I'm sure we all know what multimodal is, but just in case set definitions, multimodal basically means that we are using multiple types of data or modalities. So example, we are using like text, image, video, audio, and then we pass that through your retrieval model. So what's a multimodal retrieval? What is multimodal retrieval? So it's a search paradigm that basically enables seamless retrieval across different modalities, right? So there's like you can do like depth. Is laser pointer on? Oh, L. Okay. So there's like your depth and your heat map. You can do like IMU, audio and text, and you can these data are aligned and you can query with both of them, one of them. I'll show you an example later. So cross-modal retrieval. So you have your audio, you have your image, you have your depth, and you have your text. So you can do like embedding space arithmetic. So you take your input image and your input audio, and then you can retrieve like the whatever that's retrieved from like that from the embedding space that is close. And of course, you can also do like do unimodal retrieval, so like audio, and then you can get like generated image. So why is this important at all? So why can't I just like convert other modalities to their text representation, right? So like I have a video, I just convert it to text, and then I'll just use a normal rec system and then query of it. The first reason is because it maintains the rich and native features of each modality, right? Because let's say you have IMU data, how are you going to convert that to text? You're going to convert it to numbers, and then what you have to now you have like a tabular problem with your LLM, and now you have to like make your LLM read tabular data, have like optimizations, which is not what you want to do. So by keeping the raw modality, we don't lose this information. And also, I think in general is we just want LMs to be like more and more human like. So we use our ears to hear, we use our eyes to see, and we use our eyes to perceive depth, and of course we can read. So secondly, there's also improved performance. So ImageBind found that they actually outperform their own unimodal specialist models, and they also trump their own multimodal models. So they, if I'm not wrong, they saw a 1.4 times accuracy improvement over their audio MAE specialist model for audio classification. So it's kind of salsa, but they claim it. So yeah. So lastly, it's highly scalable. So this is quite interesting. So they have this ability to leverage like the shared representation that already exists between modalities without like retraining or like any resource intensive training. Ignore this figure for now. I'll come back to it later. Let me just show you this first. So for example, right, what they do is that they train the embedding with like a bunch of data sets that are already paired. So for example, they have the over here it says naturally aligned. So text and image, they have a text and image data set that's already paired, and then they have a image and thermal data that's already paired, which is just this. So like I guess it's like IR data, and then you have your depth and image. So what they actually found is that the model was able to produce emergent alignments, is what they call it. So like even though they were not naturally paired before, right? They were able to find that that they're still able to retrieve quite accurately with they are still able to find pairings between things that were not naturally aligned. So like text and what's this, depth, yeah, and they were able to get output from it. So going back, right, in case you're curious, I just put this because so what they found is that when they use models with stronger visual features, so VIT-B and VIT-L is just inferior clip models, and VIT-H is like a superior clip model that's supposed to produce stronger visual features. And they showed that when they tested it on their data set, it performed around like 7% better. It's just to show that the better visual model that you use, you will produce like better results. Yeah, so how does it work? I think if you see this negative log probability equation, it looks very similar to the one that Tongyao covered for DPR. Yeah, the only difference is that in this summation, there's like they're taking the dissimilar they basically say that for all patches that are not similar, they count that as a negative, so you have a larger loss from that. And I'm not really sure what it does, but I think it probably like spreads dissimilar data in embedding space, so like you have like better clustering. Okay, so I did like some unpaid work because they didn't have any diagrams on their paper, so I had to painstakingly make it on Google. So how they work is that, okay, I only have 3 data here, 3 modalities here. So image goes to a vision transformer. So actually everything is just an image. So they use a vision transformer for everything. So audio is converted to a spectrogram, which is then converted to, which is an image, and then passed to the vision transformer. For video, they take 2 seconds, they sample 2 seconds of the video, and then take like a few frames, and then convert it into patches where they pass it to the patch projection layer of the vision transformer. Yeah, so I hope they credit me.
Please go Bill Yan LeCun.
Yeah. So what's the catch, right? Like it looks pretty good. So firstly, there's a few problems with it, is that there's no cure for being ambiguous, right? For example, if you were to pass it like the picture of your clothing and then say, can I wear this for my trip to December? It's not very obvious to the LM because it doesn't have that representation between the weather and clothing. So it will just say, oh yes, it's a nice shirt, but I think it's a little too casual for a trip to Canada, which is missing the point, something a human would not have missed. Yeah, but again, this can probably be solved with like additional refining methods. So secondly, it's that right, what do I want to say for this? Right, okay, so modalities with a stronger correlation to images, they tend to perform better. So modalities that are not visual, like audio, maybe like a baby crying, will have a weaker correlation and are harder to align in embedding space. So like you think about it, a baby's cry could accompany any number of visual contexts. So it's quite hard to align this. So things that have more visual representations would do better. So like let's say temperature, probably IR data. Yeah, so lastly, so in the end, it's just a retrieval model. It has the same exact problem as like as other retrievals. So remember, Alson covered the limitations of a retrieval model. Yeah, so it has those problems as well. In that it is you still need more data to perform well in your rec tasks, and if you have too much data, you now can overshadow like the important context in your query. So there's a delicate balance there. Yeah. So this is the last slide. Any questions?
Let's thank our speaker, Winston.
All right, thank you.
Thank you, Winston. So I'm Jiaxiang. So I will be talking about training strategies, and it will be very high level. And first, I would like to give credits to the ACL 23 tutorial, which I refer a lot to when making the slides. So first, we have seen a lot of like different architectures of the like retrieval-based LLMs, and essentially this is the structure we have. On the left, we have a retrieval component, and on the right we have like a LM component. And for training, like naturally we will have like two kind of back propagations, one for the LM side, the other one for the retrieval side. But it's not that easy. First, we all know that training LMs itself is already very expensive. And for the retrieval side, since if we need to update the encoder, we will need, this means we also need to rebuild the index again. And since the index can be very huge, sometimes in terms of billions of tokens, it will be actually taking a lot of time and a lot of resources to rebuild this index as well. So more specifically, for example, like a typical when we are building a typical kind of retrieval models, we may need to encode like more than 100 million text chunks using the encoder. And as mentioned, when the encoder updated, we also need to update the index. And this reading indexing can take a lot of time because of its size. So in overall, like we can classify the training methods into these 4 categories: independent, sequential, or joint. Like joint meaning like training them together, either with a synchronous index update or with in-batch approximations. And I will maybe only focus on the 2 of them for today due to time constraints. The other 2 I'll only touch on very briefly. So for the independent training, the idea is basically we just train the 2 components independently from each other. So the pros is like we can actually do something like a plug and use. Essentially, like we can take the powerful language models and the powerful retrievers and put them into the systems, and each part can be improved independently. But the cons is LLMs are not really trained to leverage the retriever, and retrievers are not really trained to optimize for the LLM task. How about sequential training? So what does this mean? Sequential is essentially saying like we have 2 components, and the first component is first trained independently and then fixed. And then the second component is trained with objective that depends on the first one. For example, we can have a pre-trained retriever, and then we freeze the parameters, the components there, and then we train the LMs to like basically depend on the retriever. And on the other hand, we can also do the other way. We have basically we have 3 examples. On the right hand side is usually the real plug, and on the left hand side is for the real. Yeah. So I will give an example for the left hand side, which is the case of real. But actually this is in more details. Like basically we have a pre-trained, we have a retrieval model which is first pre-trained, and then we have a language model, which will do the back propagation on it. And for the retrieval model, we are going to use the stop gradient operations to basically not update it during the training. So taking at this example, retro, essentially what this do is we have a question, and for example, like this is the X is saying this is the input, and then first we will split them into chunks. For example, 3 chunks over here. And then so what we will do is it will have first have like for each of the chunks, it will be fed into a retrieval encoder, and then like basically then it will become kind of embedding, and then based on this embedding, we are going to use the KNN search like for using the index and to retrieve basically the relevant text chunks, and we are going to retrieve like top K relevant chunks. And then this will be fed into the LLM encoder. And this LLM encoder will basically, again, like embed all the relevant chunks into the embeddings. And the special thing over here below, we can see is the CCA highlighted in the transformer block. Essentially, this is what Rachel said as chunks cross attention. So what Rachel does is essentially it will additionally taking the embeddings, the E1 to E3 we have seen, and use it to compute the attention scores additionally. Yeah. And so this is how basically like we can jointly consider both the input X1 to X3 and the relevant retrieved text E1 to E3. Yeah. So if you want to compare and contrast, previously we have seen like some retrieval-based models, they put the retrieved text as part of the input. But here we are doing it. We are take the retrieved like information in the middle, basically towards the intermediate layers. And this is basically the biggest problem here. Like the index can be huge, and like it can take like 600 billion tokens given the training. So naturally, we want to just do a back propagation of like every component, but because of the size of the index, Rachel did is what we said as the sequential training. We first basically like train the retrieval components and then fix it given the training, and then update the language model size as per normal. So this is essentially an example for sequential training. So the pros, it works with, again, like off-the-shelf components. And like in either case, whether like LLMs can be trained to effectively leverage the results from the retrievers, or on the other directions, the retrievers can be trained to provide relevant text to help the LLM. However, since both components are not jointly trained together, you are still missing in the other directions. So this motivates the next part. Why not we just jointly train two components together? So there are in general like two approaches on how do we do this. The first one is asynchronous index updates. Essentially what this says is we allow the index to be still, but still I mean like outdated for a while we are updating like the encoders for the language models. So essentially, basically, but it's only going to be still for a certain period of time, which is defined by t, like a rate or frequency, refresh rate. And so essentially, like given training, if you look at the retrieval parts, the encoder will be updated, and the index will be still. And only after t steps, the index will be kind of refreshed. So look at one example like here. This is basically real, and essentially like all the same things. We just take the relevant k chunks and then concatenate this together with the input and fed to the LLM to get the final results. So what is happening? Like basically, how do we apply the idea? Is essentially at every step, the two models, the one on the left about the retrieval encoder and one on the right about the LLM is updated, and the index is only kind of refreshed at every t steps. Yeah, and in terms of implementation, essentially this starts two processes. One process is as normal to update the to do the trainings for the encoders, and the other process is like the index refresh process, which at the background like computes the updated index every t steps. And the question here is, how do we choose the index update rate? If the frequency is too high, it's very expensive. If it's too low, then we have an very outdated index, and the accuracy may drop. So in the paper, they use 500 training steps. And then they did a study that if they lower down, basically, for example, if they make it 30 times more slower, the accuracies will drop. Yeah. So the question now is, this update rate seems to be a burden. Can we don't use this? So then the other direction or the other solution is basically use in-batch approximations. The high-level idea is rather than building the full index driven training, why not just look at a subset of, for example, the training batch. And by doing kind of approximations, I can still by using some approximations, some techniques, I can still try to guarantee that the accuracy of the training will be still fine while saving time to rebuild the index. So the traditional approach is we have to re-index for a very large one. And this index approximation, essentially, we are only building the index based on the training batch. And so it's a much smaller size, and it can be computed on the fly for each training batch. The key issue is how do you ensure the training accuracies, since we are going to use this index to compute a lot of things like training loss and to optimize for our training objective. Please read the paper for more details, but we actually have covered this before. Yeah, essentially basically one way is how do you do the batching? Basically, they can use PM25 to select the most similar things together and put them in the same batch. Yeah, so this is all. So in summary, this is the table with different 4 types of techniques, and then what's the pros and cons for it. Yeah.
Okay, let's thank our speaker. I just want to say that this part, I think there are lots of open-ended questions that haven't been solved. People in IR have been dealing with outdated and re-indexing models forever. And if you think about it, any IR index has to be updated every day. Yeah. Because there are new content every day. So periodic re-indexing and then dealing with the dynamicity of the underlying corporate data is an essential part of IR. So they actually have very good methods to solve it. They just haven't made it into retrieval augmented large language models yet. So there's still quite a lot of low-hanging fruit in this area to try. I mean, just listening to the presentation, I can think about 20 things to do. Yeah, it's, nobody has all the time to do it, right? Yeah.
Question. Indexing, is there alternative solutions like, you have like in React, you have like a Wikipedia API, then you just call the API to get information from a website or something, so that you bypass having to create and build a database yourself.
You can do that for sites that want to be compliant, but usually you don't have that, like every Tom, Dick, and Harry will make their website and update it whenever they want. So it's very hard to get data pushed to you, except by providers that are very large, right? And there are things like that. Like if you have an RSS feed, you're basically saying, broadcast, hey, everyone, my web page is updated. Please take my content. But, most of the time you have to discover that. Yeah. So there are lots of approximation algorithms. Like a lot of things they'll say, okay, I know because the Israel-Hamas conflict is updating very often, so I need to sample that data more. I have to update those things. But, news about NUS, nothing ever changes here. So we don't get to update the documents on NUS at all. Okay, maybe once every 6 months is fine to check NUS. Yeah. Okay. Yeah, thanks everyone. Great session today. Let's thank all of our speakers. Okay, just one quick note. Okay, we are coming close to the end of our course. It's already week 10. We have week 13, which is the steps. And traditionally, we actually go out to dinner or supper on the last Friday of the course. Okay, so week 13, Friday, I know a lot of us are busy with finals, exams, especially our undergraduate cohort. But I will send a survey and then we can decide where to go. Don't worry, people, from my group, we still have another social separately from 6101, but yeah, hopefully that will go okay. All right, so again, steps on Wednesday on week 13 and social drinking on your own budget. Sorry, I don't have alcohol budget. That will be on Friday. Okay, thank you.
I'm wondering, what are some words like you mentioned in the IR field? Does Basically, like you mentioned, there's